Do it all the way up, maybe. Okay, so let's see how we did. The first three probably are pretty straightforward, right? Okay, anybody want to talk about any of these? Did you get all these answers?
Yes.
Okay. So the last one, what's going on with the last one? Did anybody try to look into what those are called for the homework? What do you call that sort of thing?
Hydrates.
A hydrate, a hydrate. So essentially what's going on is, let's see, do you know what kind of compound this part is right here? You like that sound? What kind of compound is that? What are our choices? Molecular or ionic, right? And why do you think it's ionic? Because it contains a metal. That's right. Metal is copper. All right, so we have an ionic compound. Ionic compounds have a property that they like to absorb water. Okay? I don't know if any of you recall the first time you saw a salt shaker with salt in it, with rice in it, right? But that's not a world thing. That's more of a human climate thing, right? On the mainland, United States, I don't know if I've ever seen it before. But come to Hawaii, we always have salt with our rice. Rice with our salt, right? Why do we do that? Okay, it helps absorb the water away from salt. Try it. Just put salt in there with no rice in it. Just stick on the bottom, it'll never come out, right? So, we call this property hygroscopic. Something's hygroscopic because it absorbs water. And you got a lot of hygroscopic stuff now that shows up in like the shoebox, sometimes in the seaweed container, or anything that you want to keep dry. Because if you keep it dry, you also keep it smelling good. Why is dryness related to smelling good? If something's dry, why does it smell okay? Because bacteria need moisture to live, right? And so if you dry it out, you put it with your shoes or whatever, it sucks up all the moisture, and the bacteria, because people are trying on your shoes a couple times before they buy them, bacteria can't grow, all right? And so it smells bad. Same thing with your armpits, right? Keep it dry, and it won't smell as bad. Okay, so this ionic compound is absorbing water. And this becomes a little bit of a problem, because if I have an ionic compound and I want to weigh out some of it and perform an experiment with it, right? I want to know exactly how many molecules or units I'm weighing out. So I weigh out a little bit of that mass on a scale. But if it was exposed to the atmosphere too much, if the lid wasn't completely tight, then some of the stuff that I'm weighing out isn't just the salt, some of it is also the what? If I have an ionic compound, here's the ionic compound, maybe I didn't draw a picture so you don't know what's going on. Here's an ionic compound that's in here, right? It says right there, copper sulfate, there it is, okay? I'm opening up the lid, and I'm getting out from inside here, pulling some out, and I'm going to put it on a weigh boat and weigh it. Right? On a little pile. If this lid was not shut well, then the surface in here is going to be doing what? Absorbing water. So when I weigh some of this out, I'll have actually weighed out on the surface what? Some water. So it looks like it says I got 1.032 grams, but in reality, some of that's water and some of it's the copper sulfate. So that becomes a mess because, I want copper sulfate, how in the world am I going to get it? Or I want a specific salt. Salt is another name for an ionic compound. Okay, not just a salt or the salt like table salt, but anything that's an ionic compound is also called a salt. So I want a specific salt, I want just the salt, but now I have all this water associated with it. So how do I fix that? What I do is I expose it to all the water that it can take. Right? Just moisture in the air. Tumble it around, shake it up, and then it absorbs all the water. And then I can include that in the formula, and I weigh out the appropriate mass that I want, taking this whole thing into account. Okay? So this is a hydrate. It means that for every unit of the salt that I'm interested in, there's 5 water molecules. Okay, so if I want to know how many oxygens are in this whole thing, there's how many on this side? And how many on this side? 5. Total? 9. If I had 2 units of this stuff, how many oxygens would there be? 18. Right? 9 times 2. Does that make sense? Excellent. So, who got those values right? Raise your hand if you got them right. Who can get them right now that we had that discussion? Excellent. Anybody have any questions about that? You can take a hydrate and you can heat it up and you can remove the water. All right, that's possible. All right. Now, different classifications of matter. Matter can be broken up into pure substances where we're talking about compounds and elements, right? We had elements up here, I just erased it not too long ago. But compounds and elements. What was our list? What were some elements that we had on our list here? Gold, silver, helium. Okay, lots of different elements on there. So compounds and elements are all pure substances. Pure substances. So water, if you have a container of water, right? I mean, if I go to the tap and fill up some water, that's not a pure substance. We had that conversation last class, right? But if I have a container that says H2O and it says pure, right? I mean, not a container from the store, but one from the lab, or if it says DI water, which means deionized water. So all the ions are pulled out. That's going to be a pure substance. Okay? Other pure substances that you deal with, we talked about helium. Helium can be a pure substance, it's elemental. When we think of a compound that's a pure substance that we do deal with. Any ideas? I couldn't think of one last class.
Oh, it's a pure substance.
Yeah. Pure substance that's a compound that we deal with. No, bleach is a solution of sodium hypochlorite water. But that's a good idea, that's a good point, something in the chemical end. Baking soda, yeah, baking soda. Not baking powder, but baking soda. Baking soda should be all sodium bicarbonate. It's good. Who said that one? Good. Any others? I think that's about it. Well, sugar would be pretty good. Sugar, so we're looking for stuff we bake with. Sugar, sodium bicarbonate. Potassium hydroxide? Nitrate? Yeah, that's a pure substance. You deal with that, getting the roots out or something, or what do you do? Stump removal, yeah. Okay. Usually, though, the things that we're talking about are this side. The things that we interact with in nature are on this side. And that's because these elements aren't generally really stable by themselves. They like to find ways to stabilize themselves by interacting with each other. So, some examples of mixtures. Milk. What's the main thing in milk? What's the, what we call the solvent? The component that's the most. And this is a hint. This is about all you drink, right? Water, right? Humans drink water. We drink it in the form of salty water, in the form of sugary water. What's the component in milk that makes it not look like water? It's a tiny bit of calcium. It's fat and protein. Fat and protein. Okay? Anybody milked a cow recently? When you milk a cow, you get a bucket full of stuff, right? This is all really frothy on top. But down here, it basically looks like a piece of ice with a little bit of water, and you mix it around and gradually melt it, right? It looks really watery, okay? And in the old days, when you would buy your milk, and people would come and deliver it to your door, the milk would be separated from the cream, and the water would be separated from it. So you take it and shake it before you put it down. That wasn't my old days, that was before me. My old days though, that's what you had to do with salad dressing. You had to shake it really good, and you had to put it on fast because it separated pretty fast. You had oil and vinegar in there, and then somebody invented ranch, which was Hidden Valley Ranch, and it was, oh, how exciting. And then they put Hidden Valley Ranch in a bottle. But what, it's not hidden anymore. It was a catastrophe. But these were things that were mixtures. But now, milk, you don't buy separate, right? You buy it homogenized, which means it's been mixed for you. And they use such a strong mixing method that it stays homogenized for a significant amount of time, for the life of the milk. If you take a cup for it and put it on the table and let it set for days, it will separate, right? Separate back out. Okay, same thing with salad dressings. I mean, rarely you see a salad dressing that you have to shake anymore. That's all chemistry, channel people. Okay. So, heterogeneous and homogeneous. Homogeneous or homogeneous, right, means that everything in the mixture is evenly dispersed, right? If I go to the top of the mixture, here's some homogenized milk now, okay? If I go to the top of the mixture here and look, I'm going to find some water molecules, I'm going to find some fat, some protein. If I look at the bottom, I'll find some water molecules, fat, and protein, and the ratio of the different components are going to be the same here and here. That makes this what? Homogeneous, right? Homogeneous. All right? If I go here and look at the fat, it's going to be much more than down here, right? Much more water down here than there is up here. So this would be a heterogeneous mixture. All right, guys, we've learned a lot today, right? So we'll see you guys on Monday. I have a little bit of time right now, so I'm going to come up here and talk about some questions that you missed. Make sure you take your exam, or sorry, your quiz, and make sure that if you want